Welcome to the course on 3G, 4G wireless mobile communication systems. In the last lecture, we completed the analysis of the CDMA multi-user downlink SNR. We looked at that expression which is given over here, which said the SNR is proportional to the spreading gain. It is proportional to the magnitude of the multipath channel between the user and the base station, between the base station and the user, that is this norm H0 square, which represents the diversity. It is proportional to the power, and in the denominator we have the multi-user plus multipath interference plus thermal and additive white Gaussian noise. So, this is the comprehensive multi-user SNR on the CDMA downlink. We also looked at the CDMA uplink situation, which is shown here. However, uplink is slightly different from the downlink, because in the uplink the signals corresponding to different users traverse different channels and add up at the base station. Hence, this situation is slightly different from the downlink. However, the expression for the downlink can be suitably modified now. Instead of having some power into norm H0 square, each power is affected by norm HK square, where HK is the channel corresponding to user K. That is the only change. So, except that the expression is more or less the same. However, there is another challenge in uplink now, because different users are at different distances. That is what we said, because different users are at different distances, hence the propagation delays for the different signals are different. Hence, the signals at the base station are asynchronous, that is, if you look at their edges, they are not synchronized. And to analyze this situation, we had to derive the asynchronous cross correlation between the sequences, or the asynchronous, the power variance of the asynchronous interference, and we said the variance of asynchronous interference is 2/3 over n. This also falls as 1 over n. In fact, it is less than the synchronous interference, because of more randomness it is 2/3 n, and then we simply derived the asynchronous uplink multi-user SNR as n norm h square p naught, except that the multi-user and multipath interference are replaced by a factor 2 over 3. That is the only difference between the synchronous and the asynchronous link. That is, the power, the variance of the multi-user interference is reduced by a factor 2/3. That is because of the asynchronous nature. And finally, we looked at an example of a CDMA system. All right. So, that is where we stopped in the last lecture. Now, let us continue with today's lecture. Today, before I move on to a new topic, let me finish one last minor topic in CDMA systems. That is, I want to talk about one last topic, that is the near far problem. That is the near far problem in CDMA systems. Now, we know that in CDMA systems, the SNR, let us consider a simple 2 user CDMA system. Consider a 2 user system. We know that the SNR is given as, the SINR at user 0 is given as P naught divided by P1 by n plus sigma n square divided by n. This is the multi-user SNR in a CDMA system. Depict that scenario over here. So, I am considering a base station. Now, in this base station there is user 0 who is at a distance d0, and there is a user 1 who is closer to the base station at distance d1. All right. So, user 1 is closer to the base station compared to user 0, such that d0 equals square root of n times d1. Let us consider a situation where d0 is square root of n times dn. We know square root of n is the length of the CDMA spreading sequence. So, user 0 is at the edge of the cell, he is much farther compared to user 1 who is closer to the base station. That is the situation we are currently considering. Now, we also know that as the distance at a distance d, let us say the transmit power of the base station is d, then because of path loss, the power, the transmit power decays as a function of 1 over d square, that is if the transmit power is Pt, at a distance d the power received is Pt over d square at, so let me write that, at distance d the power received equals Pt over d square, which implies since P0 is at a distance d0, the power received P0 is Pt over d0 square and P1 equals Pt over d1 square. However, d0 is square root of n times d0, hence P0 is nothing but Pt divided by n times d1 square, since d0 is square root n times d1. Now, when we write the expression for the received SINR at user 0, the SINR equals P0 divided by P1 over n plus sigma n square over n. I will substitute for P0 and P1 in this expression and I will write SINR equals Pt over n d1 square plus Pt over n d1 square plus sigma n square over n, and this can be simplified as Pt over Pt plus d1 square sigma n square. Now, you can see from this expression both the numerator signal power is Pt and more importantly the denominator is also Pt. So, what is happening is because user 0 is at a much larger distance compared to user 1, his received power is very small. In fact, because of the choice of distances, I constructed this distances keeping this expression in mind. In fact, from our choice of distances, it is so happening that because user 1 or user 0 is root n times the distance of user 1, his power is 1 over n times the power of user 1, which means he is essentially losing all his spreading gain. So, now the signal power and interference are both the same magnitude. If you can look at this expression, the signal power and multi user interference are of same magnitude, which means the interference is very high compared to the multi user compared to the signal power, whereas previously the interfering power was suppressed by a magnitude of n. Now, because one of the users is much farther compared to the other user, his received power is very low, hence interference is very high. This is known as the near far problem in CDMA. So, this is precisely the near far problem in CDMA, where a user who is closer to the base station, because he is transmitting his received power is much, his power is much higher, drowns out the power of the farther user, alright, or the user who is farther from the base station. So, even though, so user 1, so in the previous situation user 1 who is closer to the base station, he sort of drowns out the power of user 0, that is he causes very heavy interference, that is there is that is there is very heavy interference at user 0. This is termed as near far probable. Hence, what is essential in every CDMA system is that to the closer users you have to transmit lower power compared to the users who are farther, to whom you have to transmit more power. This is known as power regulation or power control. Hence, in a CDMA system, the power transmitted to different users has to be regulated. Hence, in a CDMA system, the power transmitted to different users has to be regulated, and this is termed that this process of regulation of the power, this process of transmitting more power to the farthest users and less power to the users who are closer to the base station is termed as power control in CDMA system. This is termed as power control in CDMA systems. Hence, power control is a key part in 2G CDMA systems, that is IS-95 based CDMA systems, 3G CDMA systems, the release 99 sort of systems. Power control is an extremely important part of any CDMA system because of the multi-user interference nature of the CDMA system. If there is no power control, then the users who are close by will drown out the signals of the users who are farthest. Hence, it is important to transmit, to regulate the power so that the users who are close to the base station have lower power compared to the users who are farther from that base station to whom you have to transmit less power. This is known as power control, and power control is a critical part of every CDMA system. So, power control, let me make that final point. Power control is a critical part of CDMA wireless systems. To avoid the near far problem, power control is a critical part of every CDMA system. Alright, so with that we will essentially conclude our discussion of CDMA, that is code division for multiple access. We have seen several topics in CDMA, starting from things such as code sequences. So, if I were to list the topics that we have seen in CDMA we have covered the following topics. CDMA stands for code division for multiple access. It forms the basis for all 3G technologies such as UMTS, CDMA 2000, HSDPA and so on. And we have seen CDMA, several different properties of CDMA, starting from the orthogonal spreading sequences or orthogonal code sequences. We looked at PM sequences and linear feedback shift register, that is linear feedback shift register, that is linear LFSR, linear for generation of PN sequences. We have seen the linear feedback shift register operation for generation of the PN sequences. Then we had seen the correlation properties of PN sequences. and that helped us characterize the SINR, that is a simple multi user SINR of a CDMA system. We also looked at the advantages of CDMA, which are A, which is jammer, we said that CDMA helps in jammer rejection, that is suppressing of malicious user who are trying to disrupt communication by trying to transmit a signal of very high power and jam your signal. We have seen that CDMA helps in jammer rejection. CDMA also helps in interference distribution and graceful CDMA helps in interference distribution and graceful degradation, which leads to universal frequency reuse. We have seen that because of universal frequency reuse, every CDMA frequency band can be used in every cell, thereby greatly enhancing the capacity of a CDMA system. Hence, CDMA leads to universal frequency reuse. And we have seen the fourth advantage is multi path diversity. CDMA can extract multi-path diversity through the rake. This is a very important advantage of a CDMA system, where previously the paths were combining beyond our control, resulting in a deep fade. In a CDMA system, because of the construction, you can isolate each path, combine these paths coherently through the rake receiver to extract diversity. This is a very important aspect. This is known as multi-path diversity. Following this, we derived the multi-user downlink SINR of CDMA. We also derived the multi-user uplink SINR. We also derived the multi-user asynchronous uplink SINR, and finally we looked at a problem of CDMA system, which is the near far. We looked at the near far problem in CDMA. We looked at the near far problem in CDMA systems, where a user who is closer to the base station can drown out a user who is farther from the base station if the power is not regulated. This leads to power control. So, we have looked at several topics and comprehensively analyzed code division for multiple access systems. So, urge you to go back, look into the notes and look into the lectures to understand this a little better, especially given the fact that CDMA expressions are fairly complicated. The expressions for multi-user SNR on the downlink, uplink, and especially the asynchronous, they are all slightly complicated. Even though intuitive, they are slightly complicated. So, I urge you to again spend time trying to understand this better. So, with this we will move on to the next topic in this course, or the next module, that is a very important topic, which is, or a module, which is MIMO. It stands for MIMO. So, this is going to be abbreviated as MIMO, which stands for multiple input multiple output. So, MIMO stands for multiple input multiple output, that is MIMO, or often called MIMO wireless system. So, we are going to discuss MIMO, the properties of MIMO wireless communication systems. That is the next topic we are going to talk about. So, what is MIMO? What is the definition of MIMO? Let me write the definition MIMO systems are a special class of wireless systems which have multiple antennas at both the transmitter and the receiver. So, MIMO systems have multiple antennas at the transmitter and receiver. So, MIMO systems possess or have multiple, that is the keyword, multiple antennas at the transmitter and receiver. As I said, this is the keyword multiple, which means greater than one, that is 2, 3 and so on antennas at both the transmitter and receiver. That is the definition of a MIMO system, that is they have multiple, more than one antenna at the transmitter and the receiver. So, now conventionally, as you know, a transmitter has a single antenna, a receiver also has a single antenna. This is known as a single input single output system. However, now you take the same transmitter and put multiple antennas on it, and you take the same receiver and put multiple antennas in it. So, the transmitter is still a single transmitter, the receiver is still a single receiver. However, only the number of antennas is increasing. Alright, this is not to be confused with situation where you have multiple transmitter. It is the same transmitter on which you are placing multiple antennas, same receiver on which you are placing multiple antennas. This is known as a MIMO system. So, let me describe it schematically. Let me draw a simple schematic diagram of that. I have a transmitter block, and previously I had one antenna. Now I have multiple antennas. Similarly, I have a receiver block. This I will abbreviate as RX, and I have multiple antennas. Each of these triangular elements, each of this represents an antenna, and the transmit block has multiple antennas. This is the receiver block has multiple antennas. I will call the number of transmit antennas as T. So, there are T transmit antennas, and there are R and there are R receive antennas. There are T transmit antennas and there are R receive antennas. This is just for the sake of clarity, let me write down this as the transmitter and this as the receiver. So, there is a transmitter, there is a receiver. The transmitter has T transmit antennas and the receiver has R receive antennas. Now, as we have already seen before, in the case of receive diversity, that is, we consider a system which has multiple receive antennas. Having more antennas provides diversity in the system. So, I will write that down as there are multiple antennas we simply said multiple antennas means multiple links, hence it means more robustness to fading, hence it leads to diversity. As there are multiple antennas, this MIMO can be employed for diversity. MIMO systems can be for diversity. Again, as there are multiple antennas, and we had seen this earlier, since there are multiple antennas, there are multiple links. So, we can advantageously employ that to protect against fading, that is by extracting diversity gain from this system. That is something we had already seen in the case of, we have not seen it in the case of multiple transmit antennas, but we saw a case where there is one transmit antenna multiple receive antennas, we said that is a receive diversity system and it can be used to extract diversity. Similarly, now we have multiple transmit antennas also, so you can use that to gain diversity. However, something very different in when you have both multiple transmit and multiple receive antennas is the following. Now, you can not only gain diversity, but you can actually increase the data rate by transmitting several information streams in parallel. So, now you can also increase the data rate. Another advantage, MIMO can increase the data rate by transmitting several information So, MIMO can increase the data rate by transmitting several information streams in parallel. That is, I can transmit on the same frequency at the same time, because I have multiple antennas. I can transmit several information streams between the transmitter and receiver in parallel, and in fact at the same transmit power. So, I have to quantify this. This is also at same transmit power. It is as if I am taking this space and multiplexing different information streams across it. That is, between the in the space between the transmitter and receiver, I am multiplexing parallel information streams. Hence, this is known in the context of MIMO as spatial multiplexing. So, this is known as spatial multiplexing, which literally means multiplexing parallel information streams, multiplexing parallel information streams in space, which is essentially multiplexing these information streams in space. So, this is known as spatial multiplexing, and that results in a tremendous increase in the data rate, which is a unique aspect of MIMO systems. Hence, it is a key aspect of any 3G and also 4G wireless systems, because as we said in the very beginning, 3G, 4G wireless systems are broadband systems characterized as having high data rates. Hence, MIMO is a key technology which in fact helps push up the data rates on this 3G and 4G wireless systems. Hence, it is a key component of 3G, 4G systems, and we are going to spend sufficient amount of time trying to understand the different properties and the different aspects of MIMO systems. So, to just schematically describe spatial multiplexing, I have a transmitter, I have the receiver, and I am transmitting multiple information streams I1, I2 up to IN. That is, these are the multiple parallel information, these are the parallel information. So, these are the parallel information streams that we are transmitting. This is a schematic. We are going to see the exact technique as we proceed through the contents of this topic. We are going to see how it is possible to in fact transmit multiple independent information streams from the transmitter to receiver in a MIMO system, and that is a very unique aspect and a very big advantage of MIMO, or a multiple input, multiple output wireless communication system. And let me just mention, this is possible to complex multidimensional signal processing. This is possible through multi-dimensional signal multi-dimensional signal processing. So, let us start with a basic description of MIMO. Let us start with getting a basic description of MIMO. In a MIMO system, I have T transmit antennas. So, I am transmitting T symbols from the T transmit antennas. Let me denote the symbol transmitted from the first transmit antenna as X1, the second transmit antenna as X2, so on and so forth up till the Tth transmit antenna as Xt. This is a vector x bar, where X1 denotes symbol from transmit antenna 1, the symbol transmitted from transmit antenna 1, X2 is from transmit and Xt is from transmit antenna T. So, there are three T symbols being transmitted from the T transmit antennas in parallel. These pass through the MIMO channel. This is the MIMO channel. So, I am transmitting T transmit and T symbols X1, X2, Xt from the T transmit antennas. This is a vector x bar of T dimensions. There is a T dimensional vector x bar passing through the MIMO channel. At the receiver, I have R receive antennas and I receive Y1, Y2 up to YR at each of the receive antennas. So, at the receiver, I will denote the received symbols as Y1, Y2, so on up to YR, where this is the vector Y bar and Y1 is received at receive antenna, Y2 is received at receive antenna 2, YR is received at receive antenna R. Alright, so I am transmitting a T symbol vector across the T transmit antennas, goes through the MIMO channel. At each of the R antennas, I am receiving Y1, Y2, YR, that is an R dimensional vector. So, x bar is also known as the transmit vector and Y bar is also known as the receive vector. So, in this system, x bar is also known as the transmit symbol vector and Y bar is also known as the receive symbol vector. Okay. So, now I can represent this as follows. There is an R dimensional vector that is received, a T dimensional vector that is transmitted. So, it must somehow go from a T dimensional transmit vector to an R dimensional receive vector, which means it is passing from a T dimensional space through to an R dimensional space. Hence, we know that this sort of a transformation can be represented by a matrix, and that is what I am going to represent it as. So, I have the R dimensional receive vector Y1, Y2 up to YR, which is some matrix times x1, x2 up to xt. This is T dimensional, this is R dimensional. Hence, we know that the matrix has to be R cross T dimensional, and that can be represented as follows: H11, H12, so on up to H1T, H21, H22, so on up to H2T, so on up to HR1, HR2, so on up to HRT. This is the R cross T dimensional matrix. This is also known as the channel matrix. Each entry of this channel matrix is a flat fading coefficient. Alright, H11, H12, H21, all these are flat fading channel coefficient. So, each of these are flat fading each of these is a flat fading channel coefficient. Now, let me just explicitly write out what y1 is. Y1 equals h11 x1 plus h12 x2 plus so on h1t xt. Hence, you can see each of the transmit symbols x1, x2 so on up to xt interferes at y1. So, all the t symbols, so x1, x2 so on up to xt interfere at y1. Similarly, the signal y2 at receive antenna 2 can be expressed as h21 x1 plus h22 x2 plus h2t xt, and you can see again x1, x2, x up to xt interfere at y2 or at receive antenna 2. Hence, x1, x2, xt interfere at receive antenna 2. So, x1, x2, xt interfere at receive antenna 1, they interfere at receive antenna 2, and they interfere in fact at each of the R receive antenna. So, the net signal that you get at each of the R receive antenna contains a component from each of the transmit antennas. So, each of the transmit antennas goes through the channel, the signal from each of the transmit antenna is received at each of the received antenna. So, it's a mingled signal from each of the transmit antenna that is received at across the R receive antennas. That is the system model. In fact, now we can say that Hij, if you look at this expression, H11 is the channel between x1 and y1, which is transmit antenna 1 and receive antenna 1. H12 is the channel between x2 and y1, that is transmit antenna 2, receive antenna 1. H21 is the channel between x1 and y2, that is transmit antenna 1 and receive antenna 2. Hence, we can say that Hij is the channel between or the channel coefficient between the ith receive antenna and jth transmit In fact, if you look at H11, that is transmit antenna 1, that is transmit antenna 1, and that is receive antenna 1. H21 is, I am sorry, this has to be the other way around. This is Rx antenna 1 and Tx antenna 1. H21 is between Rx antenna 2 and Tx antenna 1. Hence, between each of the R receive antennas and T of the transmit antennas, there is a flat fading channel coefficient. Hence, there is a total of R times T channel coefficient. Hence, total of RT channel, hence there is a total of RT channel coefficients. And the MIMO channel matrix, as we already said, is represented as the MIMO channel matrix is nothing but H equals H11, H12, H21, HR1, H1T, H2T, HR2, so on up to HRT. This is the R cross T dimensional MIMO. This is the R cross T dimensional MIMO channel matrix. Hence, the MIMO system model can be expressed as follows. So, we said that the channel matrix is R cross T dimensional. It contains R T elements, which are the coefficients between each of the transmit and receive, and each receive and transmit antenna pair. Since there are R receive antennas and 3 transmit antennas, there are a total of R times T pairs, and this channel matrix is hence RT dimensional. So, now let us go to the MIMO system model. The MIMO system model can be described as follows: Y1, Y2 up to YR equals H11, H12, H21, so on, that is the channel matrix HR1, so on, H1T, so on up to HRT times X1, X2, XT, that is the received vector is matrix H times transmit vector, plus of course, there is going to be noise, which is N1, N2, NR. Each of the receive antennas there is going to be noise. So, N1 is the noise at receive antenna 1, N2 is the noise at receive antenna 2, so on unto NR is the noise at receive antenna R. So, I can represent this as Y bar equals matrix H times X bar plus N bar. So, let me write this down again succinctly over here. Y bar equals H X bar plus N bar. Let me again label each of these components. Y bar is the R dimensional, this is the R dimensional receive vector. H is the R cross T dimensional channel matrix. X is the T dimensional transmit vector, and N is the R dimensional hence I have Y bar, that is R dimensional receive vector, equals H times X bar plus N bar. Y bar is the R dimensional receive vector, H is the R cross T dimensional matrix, X bar is the T dimensional transmit vector, plus N bar, which is the R dimensional noise vector. And a word about the noise. Now, the noise is a vector, and this vector noise can be described as follows. Let us look into before we proceed into noise, let us look at some special cases. Now, if R equals, or if T equals 1, we have a special case, that is number of transmit antennas equals 1. We have a special case that we have seen before. We have Y1, Y2 up to YR equals H1, H2. Since there is only one column of coefficients, I am going to represent it by H1, H2 up to HR, that is H1, H2 up to HR, X plus N1, N2 up to NR, the noise at each receive antenna. This we have seen before. This is Y bar equals H bar X plus N bar. This is also the essentially the receive diversity system. We have seen this before in our discussion on diversity. This is a receive diversity diversity system, and in the context of MIMO, this is known as, look at this, I am transmitting a single symbol, I am receiving R symbols across the R receive antennas, hence this is single input multiple output, hence this is also known as the CMO or a single input multiple output system. Hence diversity system is also termed as a CMO system, where CMO stands for single input multiple output. CMO also stands for single input multiple output. This is termed as a CMO system. Let us consider the other special case, which is T equals 1, which is R equals 1 and certain number of transmit antennas. In that case, we have Y equals H1. So, we are considering the case where number of receive antennas R equals 1. We have not seen this case before, and Y equals, now since I have many transmit antennas, 1 receive antennas, I have a row, and this can be represented as Y equals H1 H2 up to HT times X1 X2 up to XT plus N. This is the same as H bar transpose X bar plus N. So, now I am saying there are T transmit antennas, but only one single antenna, hence the channel matrix is now a row vector. This is known as a transmit diversity scenario or a MISO system, that is multiple input single output systems. This is also known as transmit diversity system. Also in the context of MIMO, transmit diversity is known as MISO, that is MISO system, which is multiple input single output. This is known as a MISO system, which is essentially a multiple input single output system. So, in the context of MIMO, we have two special cases. When T equals 1, we know it as a, we term it as a CMO system, that is single input multiple output. When R equals 1, we term it as a MISO system, which is multiple input single output. And now obviously the next question is a special case, what happens when both R equals T equals 1. When R equals T equals 1, we have the traditional scalar fading coefficient channel, which is Y equals Hx plus N. This is naturally termed as a CISO channel, which stands for single input. This naturally stands for single input single output, that is the traditional one transmit antenna one receive antenna system is also termed as a CISO system, which is single input single output system. Now, let us come to a slight discussion on the noise. We have said the noise is a vector n bar, which is given as n1 n2 so on up to nr. This is r dimensional vector, hence this is an r dimensional, this is an r dimensional vector. So, this noise is an r dimensional vector, that is it has r noise components corresponding to the noise component at each receive antenna. We will assume the following, we will assume that the power of each noise component Ni square equals sigma n square, that is the power in each noise component at each receive antenna, power in the noise component at each receive antenna is sigma n square. Further, we will assume that the noise processes at different receive antennas are uncorrelated, and since it is Gaussian independent, which is also a natural thing to assume because there are different receive antennas, so the noise processes are uncorrelated. Hence, we are going to also assume that expected Ni Nj star equals 0, that is a correlation between the noise at the ith antenna and the jth ith and jth receive antenna is 0. Hence, we can write now the multidimensional correlation or the covariance matrix of this noise as expected n bar Hermitian. This is also the multidimensional analog of the correlation between the noise. This is also known as a covariance matrix. This is known as the covariance. This covariance matrix is expected N1, N2, so on up to Nr times N Hermitian, which is you take transpose and conjugate, that is N1 conjugate, N2 conjugate, Nr conjugate, which is nothing but expected N1 conjugate, which is norm N1 square, N2 N1 conjugate, N1 N2 conjugate, so on up to N1 Nr conjugate. This is magnitude N2 square, so on up to Nr N1 conjugate, so on up to magnitude Nr square. Now, what you can observe when you take the expectation operator inside is expectation of an operator is linear, hence it goes inside, that each of these components on the diagonal is sigma n square, and each of these cross terms which are off diagonal are essentially 0. Hence, this matrix, which is the covariance matrix of the noise vector at the receiver, is nothing but expected n bar Hermitian equals only the diagonal terms survive this is hence equals sigma n square identity matrix. Hence, the covariance matrix of this noise is sigma n square times identity. This is also termed as being spatially wide. That is, across space, the antenna, the noise at each antenna, each pairs of receive antennas is uncorrelated, that is, it is white across space. Similarly, you know that if the antennas, if distinct samples of the noise are uncorrelated, then you know it is temporally uncorrelated. Now, we have seen the definition of spatially uncorrelated or spatially white noise. Now, if the noise is both spatially and temporally, that is, if the noise samples are uncorrelated across antennas and if they are also uncorrelated across time, that is known as spatio-temporally white noise. So, spatio white noise implies noise is uncorrelated across antennas and time, that is spatio-temporally uncorrelated noise, which has a covariance of sigma n square. We are going to denote this as R n, which is the covariance. Hence, R n equals expected n bar Hermitian equals sigma n square I. This is the covariance matrix of the noise at the receiver. So, this is the covariance matrix. So, that completes our discussion of the system model of the MIMO system model, which we have seen is consists of r dimensional receive vector, which is the symbols received at the r antennas, r cross t channel matrix consisting of r t flat fading coefficients, t dimensional transmit vector consisting of symbols transmitted at each transmit antenna plus the r dimensional noise vector, which consists of the noise samples at each receive antenna, and the covariance of that noise is given as R n is expected n bar Hermitian, which is sigma n square identity. So, with this we have set down the system model of a MIMO system. With the next lecture, in the next lecture we will study several other properties and start analyzing MIMO systems. So, because of so at this point I will conclude this lecture, and I will see you again in the next lecture. Thank you very much.